Hello, future engineers. This is Madan Mohan. And remember, engineering is not a subject, it's a passion, it's a mindset, it's a lifestyle. Today, we are discussing about boundary conditions. As you know, Maxwell's equations tell us how fields behave in space. Boundary conditions tell us how those fields behave at surfaces. We now know how electromagnetic fields are generated, but what happens when these fields encounter a boundary between two materials? That is where boundary conditions come into picture. Imagine an electric field traveling in air and suddenly meeting a dielectric material. Does it stop? Does it bend? Does its strength will change? Boundary conditions give us the answer. Fields cannot jump randomly at a boundary. They must obey certain rules. Those rules are called boundary conditions. In practical engineering problems, materials are never infinite. Every interface matters. Boundary conditions help us solve real world electromagnetic problems. Maxwell's equations give us differential equations, but boundary conditions provide the necessary constraints to unequally solve them. So far, we have seen the existence of electric field in a homogeneous medium is considered. If the field exists in a region consisting of two different media, the conditions that the field must satisfy the interface separating the media are called boundary conditions. These conditions are helpful in determining the field on one side of the boundary if we know the field on the other side. Depending upon the types of material in the media we are using, these are made up of either dielectric of two different relative permittivities, say epsilon r1 and epsilon r2, conductor and dielectric, conductor and free space. To determine the boundary conditions, we are making use of two equations of electrostatic field. One is conservative property, other one is Gauss law. So as per the conservative property, the closed line integral of E bar dot dl is equal to 0, and according to Gauss law, it is surface integral of d bar dot ds is equal to q enclosed. That is in integral form of Gauss law. So also the electric field and electric flux density, which are decomposed into two orthogonal components like E is equal to Et plus En and D is equal to dt plus dn. Here E and D are electrical field intensity and electrical flux density. So which is resolved into two components like tangential components and normal components. So if we consider the first kind of boundary that is existing between two dielectrics of different relative permittivities, we just consider the electric field E bar which is existing in a region consisting of two different dielectrics epsilon r1 and epsilon r2. Here in media 1 we are considering E1 is equal to E1t plus E1n, and in media 2 E2 is considered as E2t plus E2n, where as I said t and n represents tangential and normal components. So you can see here clearly this is the interface between two mediums. This is the first media and this is second media with the different relative permittivities. The components are resolved into tangential and normal both in region 1 and region 2 as E2t, E2n in second region, E1n and E1t in the first region. So if we apply conservative property as I said to the closed path, that is A, B, C, D, A, and assume that the path is very small with respect to the variation of E bar, we can write it as the traveling of this particular path from A to A again towards A to B, B to C, C to D and D to A. When it is traveling from A to B, it has to travel a distance of del W. When it is traveling from B to C, it has to travel a distance of delta H. In this way, we can write del W and del H. If you see here, the first term in the equation, E1t represents when it is traveling from A to B, it is in the direction of E1t with a distance of del w. So it is written as E1t del w. And if you see the second term in the equation, it is E1n. It is traveling in the direction of E1n, but it is mentioned as minus because it is exactly traveling in the opposite direction to the first media direction of normal component of electrical field intensity. We can see it is upward direction, but it is in downward direction. And when it is traveling from B to C, halfway it will travel in first region and the remaining half it will travel in second region. So it is mentioned as del H by 2 minus E to N. E to N represents the normal component of second region, which is also in opposite direction. So the total distance, as I said, is divided into two equal halves, that is del H by 2 and del H by 2. So that is about the path from B to C. If you see from C to D, it is traveling in the opposite direction to the tangential component of second media E to T. So it is again minus E to T, and the distance it is traveling is delta W. After once it's traveled from C to D, again it has to travel from D to A. So which, as I said, it has to travel half of the distance in second region and half of the distance in first region. So the total distance is again divided into two equal halves, that is del H by 2 and del H by 2. And if you see the components, both are positive because they are traveling the same direction of E2n and E1n. So it is clearly mentioned as E2n, E1n both are positive. Delta H by 2 is the distance traveled by the path from D to A. So here we can write the tangential component of electrical field intensity is the magnitude of Et, and En is the magnitude of En. As in this case, we can write that del H tending towards 0 in the first equation becomes E1t is exactly equal to E2t. So which says that the tangential components of E bar are the same on the two sides of the boundary, or in other words we can say E2 undergoes no change on the boundary and it is said to be continuous across the boundary. But now, if we see about the value of electrical flux density based on the relation between D and E, we know D is equal to epsilon E. So we can write D1T by epsilon 1 is equal to E1T and D2T by epsilon 2 is equal to E2T. So we can relate from the first boundary condition E1T is equal to E2T, and we can write it as D1T by epsilon 1 is equal to D2T by epsilon 2. Therefore, we can write D1T by D2T is equal to epsilon 1 by epsilon 2, which says that the tangential components of electrical flux density d bar is discontinuous across the surface. So if we apply Gauss law to a pillbox kind of surface, allowing delta H tending towards 0, for this surface we do have differential surface. One is on the first region, the other is on the second region. Here D1n is nothing but the normal component of electrical flux density in region 1 along z direction into differential surface del s, which is along del z, that is az. And coming to second region, the normal component of electrical flux density is d2n into az, and the differential surface is exactly in opposite direction to the differential surface of first region. So it is clearly mentioned as minus az, which is equal to del q. So this is Gauss law applied for the pillbox, which is nothing but d bar dot ds is equal to q. For the differential pillbox kind of surface, we are considering differential charge, so it is equal to delta q. So this first term in the equation represents top region and second term represents bottom region. So as you know, del q is equal to rho s into delta s. So it is from the surface charge density definition. Surface charge density is equal to charge per surface. So we are writing del q in terms of surface charge density as rho s into delta s. So rho s is nothing but charge density which is placed at the boundary. Then we can write d1n into del s minus d2n into del s is equal to rho s ds, and we can take out delta s from the left hand side and we can cancel out from the right hand side. So d1n minus d2n is equal to rho, and we have to note here that d bar is directed from region 2 to 1. The direction of d bar is from second region to first region. So if say there is no free charges existing at the interface, we can say that rho s is equal to 0, and so d1n is equal to d2n. So we can say the normal component of d bar is continuous across the surface, that is dn undergoes no change at the boundary. So we can say, based on the relation between d and e again, d is equal to epsilon e, from which we can write epsilon 1 e1n is equal to epsilon 2 e2n. So from this we can write again e1n by e2n is equal to epsilon r2 by epsilon r1. Here we can say the normal component of E bar is discontinuous at the boundary. So from this we can say the boundary conditions are used to determine the refraction of the electrical field across the surface by considering D1 or E1 and D2 or E2, making angles theta 1 and theta 2 with the normal to the interface as shown in figure. We can write E1 sin theta 1 is equal to E1t, which is equal to E2t, which is equal to E2 sin theta 2, or simply we can say E1 sin theta 1 is equal to E2 sin theta 2. Similarly, by applying other condition, as you know, D1n is equal to D2n, epsilon 1 E1 cos theta 1 is equal to epsilon 2 E2 cos theta 2. If we take the ratio of first and second equations, it becomes tan theta 1 by epsilon 1 is equal to tan theta 2 by epsilon 2. So from this we can write tan theta 1 by tan theta 2 is equal to epsilon r1 by epsilon r2. So this is the case when the values of D and E are making some angles with the interface between two areas or two medias or two surfaces. Okay. So the other condition is when the two medias are, one is conductor, other one is dielectric. So electric field intensity is 0 inside the conductor, as you know. So we can say inside a conductor E bar value is equal to 0. So if we apply here in the first region as conductor, we can take directly the value of E bar is equal to 0. So if we apply conservative property to the closure path here, again for the same kind of loop A, B, C, D, A, since the tangential components of the medium 1, that is conductor, is 0, so we can say it is 0 is equal to the terms which are related to region 1 is going to become 0. The only terms is going to be for second region because it is a dielectric one. So the same expression, wherever we are having the terms related to first region is going to become 0, and as letting delta H tending towards 0, Et becomes 0, where Et is nothing but the tangential component of field in the dielectric medium. And from Gauss law applied to the pillbox and letting del H tends to 0, we can write del Q is equal to del dn delta S minus 0 into delta. This is for the first region. So the normal component of d bar is 0 in the conductor medium. Therefore, we can write dn is equal to del Q by del S, which is equal to rho S. The ratio of charge per surface is nothing but rho S. So we can conclude that normal component of electrical flux density is equal to surface charge density rho S. So we can conclude that no electric field may exist within a conductor, that is rho v is equal to 0. Ultimately, E bar value also going to become 0. Since E bar is equal to 0, from the relation we can say E bar is equal to minus del V. We can say no potential difference between any two points in the conductor, that is conductor is nothing but a equipotential body, equipotential surface. So E bar can only be external to the conductor and normal to its surface, that is the tangential component of electrical flux density is equal to epsilon naught epsilon r into Et, which is equal to 0, and the normal component of electrical flux density is the product of epsilon naught epsilon r into En, which is equal to rho S. So that is the case for when we consider one medium is conductor, other one is dielectric. If we go for considering conductor and free space boundary, if we can replace just for a free space, we know the value of epsilon r is equal to 1. So what happens, dt is going to become, in place of epsilon r equal to 1, it is going to be simply epsilon naught into Et, which is equal to 0. And for dn also, it is equal to epsilon naught into epsilon En, which is equal to rho S. So that is all about the boundary conditions. Hope you understand everything clearly. Thank you all. Thank you.